Our objective is to practice radicals in the denominator and simplifying those, and then also working with inverses. So first of all, let's do some examples of radicals in the denominator. So this first one, as a reminder, when you have a binomial in the denominator, you're going to multiply by the conjugate. So the conjugate of this will be 5 minus the square root of 3 over 5 minus the square root of 3. This fraction is equal to 1, so when you multiply by 1 doesn't change the value, but it will change the form, so we no longer have radicals in the denominator. So multiply and distribute, you get 30 minus 6 square roots of 3. All over, when we double distribute here, we get 25 minus 5 square roots of 3 plus 5 square roots of 3. And then lastly, minus the square root of 9. Now when I simplify that, I get 30 minus 6 square roots of 3 on the top. When I simplify the bottom, you've got to make sure you take and you get rid of the two middle terms because they are opposites. And then the square root of 9, we have a minus 3 because square root of 9 is just a 3. No more radicals in the denominator. Now let's go ahead and keep simplifying. 30 minus 6 square roots of 3 all over 22. There's a common factor of 2 in every term. You have to factor that 2 out. When you factor the 2 out and then reduce it, you'll be left with a 15 minus 3 square roots of 3 all over 11. No more radicals in the denominator, and we have our final result completely simplified. Now this next one, we typically do when we have a single term in the denominator is multiply by the square root of 8 over the square root of 8. This would get rid of the radical in the denominator, but then we'd have to do some reducing. And we might have to anyway, but what I would recommend you do is if you can start recognizing that 8 goes into 16, this is already has a 4 in it, that's a perfect square. But if you just multiply it by the square root of 2 over the square root of 2, then you can make it into a perfect square and have it more reduced. So you have 5 square roots of 2 over the square root of 16, and that just gives you 5 square roots of 2 over 4. Now if you did it the other way, square root of 8 over square root of 8, you get 5 square roots of 8 over 8, and then the square root of 8 you'd have to simplify by making square root of 4 times square root of 2, and you'd end up with the same answer once you simplify. This just gets you there quicker if you recognize that the 16 is the quicker route of the perfect square. Now down here we want to get a perfect cube, so we have a 2, we need to have a 2 cubed, so I'm going to multiply by 2 squared, which is a 4, in top and bottom as the radicand. That will give me as a denominator the cube root of 8, which is a perfect cube, and on the top 10 cube roots of 4, which we can't reduce. Cube root of 8 on the bottom is going to just be equal to a 2. The 10 and the 2, the ones outside of the radical, can be reduced, and so that becomes 5 cube roots of 4 in simplified form. Okay, so that's reviewing over radicals in the denominator. Let's do some inverse function review. Let's review over a couple of these. So the first thing to find the inverse of this function, the first step is instead of having f of x equals, you make it y equals 13x minus 9 all over 11. Now you take that and you're going to swap the x and the y. So the x goes over on this side, the y goes up here. Now we have the inverse, but we don't have it in the function of form where we have the y by itself. So we're going to get the y by itself. First step, multiply both sides by 11. I will get rid of the 11 in the denominator. Then we're going to go ahead and add 9 to both sides. And then we're going to divide both sides by 13. So you get 11x plus 9 all over 13 as my inverse function. I'm going to rewrite it because we usually use this as our notation for the inverse function. That little -1 up there indicates it's an inverse function, so we'll write it as 11x plus 9 all over 13 as my inverse function. All right, and our last step here is to verify that these two are inverses. Now there's two ways to do it. There's an informal way of just taking one, finding the inverse, and seeing if it matches the other one. The formal way, which I want you to try using, is that we're going to show that f of g of x will equal x, and g of f of x also equals x. So we're going to use this method. You show this and show that g of f of x equals x. That's the formal way to do it, that we verify that these two are inverses. So first of all, I'm going to take the f function, f of g of x. I'm going to take out the x in that function, and where there's an x, I'm going to put a parentheses, and in that parentheses, I'm going to put the g of x, so 7 minus x over 2. These 2's reduce, so you end up with 7 minus 7, then minus a negative will be a plus x. 7 minus 7 is gone, and we're left with just an x. So f of g of x does equal that x. Now we also have to do it with the g of f of x. You got to do it both ways. So by doing this one, I'm going to take the g function, take out where there's an x, put a parentheses in its place, and put that over my 2. Now I'm going to put this the f function that's on the inside, I'm going to put that inside my input spot, and now I'm going to simplify these two. So you have 7 minus 7 plus 2x over 2. 7 minus 7 is gone, 2x over 2, and I verified that they both equal x. So we've reviewed over when you have radicals in the denominator, how to simplify those, and also how to find the inverse, and how to verify if two functions are inverses.